The following program is video supplemental instruction. VSI is brought to you by the Teaching Center, UF's Learning Support Center, www.teachingcenter.ufl.edu.
Okay, number 2 here is just a plethora of questions dealing with Calc 1 material. So let's just go through it step by step. You're given the function, the derivative, and the second derivative. So let me just write that out again real quick here. So our function is 10 minus x e to the x. Our derivative, in the interest of keeping these the same, I'm going to write them in the other order. 9 minus x e to the x, and f double prime is 8 minus x e to the x. So there's our function, its derivative, and second derivative. So the first part A asks us critical numbers. So what are the critical numbers of this function? Remember that the critical numbers are anything that makes the first derivative either 0 or undefined, that is defined in the function. The only thing that happens there is if x is equal to 9, because that would make our derivative 0. It's impossible to make this derivative undefined, so we would have x equals 9 as a critical number. Critical numbers are where your local maxima or minima could be. So 9 is either a maximum or a minimum, and then the other we're just not going to have any. So let's see what happens there. In this case, since you're already given the second derivative, it's easiest just to use that second derivative test. You might be more familiar with using a number line, which is fine. But like I said, since the second derivative is already here right in front of you, you might as well do that. It's going to be simpler. So at 9, the second derivative is going to be negative because we have 8 minus 9. Negative means concave down, means that this is a maximum. Which also means then we have no local minima. Okay, so part B, that was part A here. Part B asks about inflection points. So the inflection points are where your second derivative is either 0 or undefined, changes sign. That's defined on the function. In this case, it's quite obvious that we only have the number x equals 8. So inflection points, we have x equals 8. That makes our second derivative 0. It changes sign there. Okay, part C says horizontal asymptotes. So where are horizontal asymptotes? Remember, for a horizontal asymptote, that's what happens to the function as you go to either infinity or negative infinity. Well, let's see here. As we go to infinity of this limit, actually let me write this out here. Limit as x goes to infinity of 10 minus x e to the x. As we go to infinity, e to the infinity is infinity. 10 minus infinity is negative infinity times infinity. We get negative infinity. In other words, that doesn't produce a horizontal asymptote. However, if we go to, as x approaches negative infinity of this function, we're going to get infinity here. 10 minus negative infinity is infinity. E to the negative infinity is 0. We get an infinity times 0 problem going on here. But there's a couple different ways you could kind of think about this one to make it easier. At this stage, you're probably familiar with just looking at the class of functions, like a linear function versus an exponential function. In this case, like an exponential function always wins. But you can show this by L'Hopital's rule. And in doing L'Hopital's rule, we need to make this a fraction. Pretty easy to do that just by saying divided by e to the negative x. That's the same thing as multiplying by e to the x. Now it's a fraction, you can use L'Hopital's rule. So this is an indeterminate form because this would give you infinity over infinity. So L'Hopital's rule will help you solve that. So the limit as x goes to negative infinity of this is the same as the limit as x goes to negative infinity of the derivative of the top over the derivative of the bottom. So the derivative of the top is negative 1. The derivative of the bottom is negative e to the negative x. In other words, the negatives cancel out, and 1 over e to the negative x, we're just dealing with e to the x. So like I said, e to the x wins. It beats polynomial functions in terms of which one has the stronger infinity or 0. E to the negative infinity is 0. So we do have one horizontal asymptote, y equals 0. This one gave us an infinity or negative infinity. That just means the graph kept going up or going down. It never had a horizontal asymptote. Okay, part D is now kind of talking about what we were getting at here, which is where is f increasing or decreasing, concave up, concave down on number lines. So let's draw two number lines, one for f prime and one for f double prime. Since we already figured out where we had maxes and mins and where our inflection points were, this should be pretty simple because our only critical number was 9. And we said that that was a max. So the only way that could be a max excuse me, is if we went up and then down that way. Yes, because, well, we can check numbers just to be sure. If you plug in 8, we get a positive number there. And if you plug in 10, we get a negative number. So, for the double prime, 8 minus x e to the x, our only critical number there was 8. Or not critical number, our only possible inflection point was 8. Remember when you graph a number line for the second derivative, you not only put inflection points, but other numbers that could have been inflection points, meaning even if they made the second derivative 0, but didn't change sign, you still put them on there. So we can just plug in numbers on either side of that too. Of course, 7 gives you positive, 9 gives you negative. So we have that it's increasing from negative infinity to 9, decreasing from 9 to infinity. We have that it's concave up from negative infinity to 8, concave down from 8 to infinity. And the last thing we need to do is sketch the graph. So let's see what this would look like here. We know that we have a horizontal asymptote at y equals 0. And that was when we were going towards negative infinity. So it's going to be coming up from that as we were going to the left. Let me draw this a little bit more gradually. Because we need to have a maximum at x equals 9. And the exact value of that maximum, if we plugged it in here, 9 would give us just e to the 9th power, which is pretty high, so I'm not going to draw this graph to scale. So we have some maximum point here. So we just have that we're always concave up until we get to 8, which is right before that. So this graph is going to be increasing slowly, concave up. Right when we get to 8, now it's going to switch to concave down. I drew that off the screen there. But in any case, we're going to be going down after that to infinity. Because as we went to infinity, furthest to the right, our limit just went to negative infinity, which meant we just keep going down. So right here at 8 is our inflection point. At the top there is our max. So you can see that works there. We have concave up. Right here it's concave down the rest of the way, so that works. That's the highest point, that's our max. It's decreasing the rest of the way. So that works there. And all of our other conditions are satisfied. We have this horizontal asymptote here at y equals 0 going to the left.
The Teaching Center, UF's Learning Support Center, www.teachingcenter.ufl.edu.